Let's build a Monte Carlo simulation in Python to help you see where the crypto market price might go up. But before we get started, what even is Monte Carlo? Well, the Monte Carlo simulation runs the same model thousands or even millions of times with different random inputs affecting it and collects all of the outcomes to show the range of possible results for your assumption. And today, we'll be building a 5-coin crypto portfolio and simulating its possible trajectory 5,000 different times. So let's get coding. As with every Python model, we start by importing our libraries. We have NumPy for math, Pandas for data, Y-Finance to reach out to Yahoo Finance and load in some data, and Matplotlib to make a pretty cool visualization later on. And now that we have those libraries, it's time to actually decide what coins will be a part of our crypto portfolio. And these are all priced in US dollars. The weights vector says how much of $1 we can allocate to each coin. So the 0.4 you see means 40 cents of each dollar goes into Bitcoin. 25 cents of each dollar will go into Ethereum, and so on and so forth until all 5 coins together sum to 1. And now when it comes to the Monte Carlo simulation, we first simulate the price path of each individual coin. And then these weights are the recipe we use to blend those 5 separate simulations into a single combined portfolio. Now the way we choose these initial weights are purely a stylistic choice. I chose to give bigger slices to Bitcoin and Ethereum because they're dominating the crypto market right now, and then gave some smaller slices to the rest of the tickers. Now here's where we actually load in our data. The code reaches out to Yahoo Finance and grabs 2 years of daily closing prices for all 5 tickers at once. From these raw prices, we compute those daily returns, which tells us how much the coin price has changed from the last closing date. Then we save the mean of all these daily returns in a variable called mu, and that represents the average daily drift the Monte Carlo process will lean towards when it projects prices into the future. The covariance matrix measures how noisy each coin is on its own, and more importantly, how 2 coins move together. So that's volatility and correlations in one object. And then S0 takes the very last row of all the closing prices and uses it as a starting point for every simulated future. So whether you're running the code today, tomorrow, or next month, day 0 begins with the most recent data. Now here we're defining the start of a function called simulate portfolio paths, and this is the heart of the Monte Carlo engine. Here we define d over t as 1 over 365 because each step in the simulation is 1 day, and 1 day is 365ths of a year. And we define it this way simply because the motion formula we'll be using later on defines all of its units in years. And the assets variable simply takes the length of all of our closing prices to figure out how many tickers we're working with, which is 5. So now in Monte Carlo, we add a small shock to the price at every step in the simulation. And this is a random shift, whether it be up or down to the dollar amount, to account for everything unpredictable in this world. News, emotions, and other illogical things that could move the crypto market up or down. And in our simulation, we need random shocks that are not only noisy but also correlated, so that when something happens, all the tickers will tend to move together like they do in real life. But to fix this problem, we use something called Cholesky decomposition. And this takes our covariance matrix with random independent numbers and turns it into a matrix full of correlated shocks that match the covariance structure we estimate. Now for the paths variable. You can think of this as a giant 3D spreadsheet that stores the whole story of the simulation. The first axis is time, so which day we're on. The second axis is which coin we're talking about. And the third axis is which alternate universe or scenario we're actually in. So that's scenario 1, 2, 3, all the way up to scenario n. So pulling any specific path means the price of coin X on day Y in simulated world Z. And now we can actually simulate using a for loop. So essentially, every simulation of the for loop represents one step forward in time across thousands of possible future situations all at once. Now in this model, we're using geometric Brownian motion, and that's just a fancy name for a price model that says prices tend to drift in some average direction but are constantly shaken by the shocks around them, which is fairly logical. In our loop for each day, we first create Z, which is a grid of random numbers. And this is the raw noise that's hitting each coin on each day of the model. But then we multiply Z by that Cholesky matrix from before so that the noise is no longer independent but correlated. And then we're applying all the parts of the geometric Brownian motion formula in Python. Then we apply it to the paths variable. And this means each new row of paths is the simulated prices for all the coins in all universes 1 day further into the future. Once we have all those simulated prices, we collapse them into a single portfolio. Essentially, we say multiply each coin's price by its weight and add across all the coins for every single time step and every single simulation. The result is the full evolution of our total portfolio in thousands of parallel possible universes. And we return both the paths and these portfolio values. And now it's time to finally simulate with real numbers. We plug in our prices for for today and lots of other parameters that are specific to our situation. So here the model is saying, given what the past 2 years looked like, here are 5,000 plausible ways the next 6 months could unfold for you under this portfolio. This is what we will use to summarize the risk and upside in a probabilistic way. So now to summarize, the percentile calls here treat final values like a big empirical distribution and pick out 3 landmarks. 10th percentile is the level such that only 10% of simulated outcomes end up below that number, so it plays the role of a pessimistic but not impossible bear case. The 50th percentile is simply the median, meaning half the simulations are below it and half are above it. And it tells us the typical outcome according to our model. And the 90th percentile is the bullish scenario that represents all the outcomes that appear in the top 10%. When we print these 3 numbers together, we get a plausible outcome for our portfolio's behavior over the next 180 days. And finally, here is the code for the visualization for this Monte Carlo simulation. The plot takes the first 200 simulated portfolio paths and lays them on top of each other. So every single line is a different possible trajectory for our 5-coin portfolio. And that is a Monte Carlo simulation coded in Python for you right in front of your eyes. The full code is linked right here, so if you learned something from this video, then don't forget to save it for later and follow for more.